Today's lecture is going to be introducing our next chapter, chapter 10, where we're talking about VSEPR theory, which is building off of our Lewis structures. And so in order to talk about VSEPR theory, we want to go over and make sure we remember our bonding. And so when you're looking at this, let's go through and let's decide which of these is going to be an ionic bond or a covalent bond or a metallic one. And so remember what we're looking for when you want an ionic bond is we want a big difference. We want a metal and a non-metal. Right? So that takes out water because water is two nonmetals, takes out glucose, which is all nonmetals, as well as nitrogen dioxide. And then aluminum is just metal. So that doesn't work for us. So our answer is going to be E, calcium carbonate. We have the metal with the calcium, and then we have the polyatomic ion carbonate. Another good way to look for ionic compounds is if you see a polyatomic ion, then we are going to be in an ionic compound because polyatomic ions are already ions. So the force holding them together has to be that charge. Looking at our next one, which one of these will have the highest lattice energy? When we think about it, our lattice energy is going to be related to our bond strength between our ions. And so we're looking for something that has a small radius as well as a large charge. Now, all of these have bromine on one side, and so we would really just comparing potassium versus lithium versus sodium and rubidium. Now, they all have the same charge, and so you might be tempted to say that they all have the same lattice energy, but we have to take into account size. So the smaller the size, then the higher the lattice energy. And when we talk about size, we're really talking about the radius. So between those four, lithium has the smallest radius, and that's going to give us our smallest size. This is looking at the definition of what a lattice energy is. So take a moment, go ahead and try to think about what your lattice energy is, and let's put that equation together. Now, lattice energy is when we take our separate ions in their gaseous state, and we turn them into a solid. Similar to this expression right down here. So if we're looking for our lattice energy of AlCl3, then we should have aluminum as its ion, so Al3 plus, and 3 chloride ions coming together. So this is going to be our lattice energy. Go ahead and draw out your Lewis structure for xenon I2. And we're trying to think about how many lone pairs we have on xenon. Now, I'll give you a moment to do that, and then we'll go through that. Right, so we start with our bond skeleton. We also know that we should have 8 valence electrons from the xenon. Each iodine has 7, and so we should have a total of 14 plus 8. So that's going to be 22 valence electrons. We start on the outside. Right? That takes away 12 plus 4 from the bonds. We have 6 left over. We should put those on the center one. And if we look at xenon, xenon is large enough to have an expanded octet, so that is fine. And so when it asks us how many lone pairs there are, then we should have 3. There's 6 unbonded electrons. And if we pair those up, because it says pairs, then that's how we get 3. Go ahead and choose your best Lewis structure for CS2. Now remember that CS2 should have 4 plus 12 electrons, so we should have a total of 16 electrons. We want to start looking for octets, right? And this one has an octet. So when we look at the top one, carbon has an octet, but our sulfurs have an expanded octet. Sulfurs can have an expanded octet, but this is too many valence electrons. This is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 valence electrons. So it can't be that one. 2, 4, 6, 8, 10, 12, 14, 16. So B has the correct number of valence electrons, but sulfurs don't have an octet. So that one's probably not going to be our best option either. 2, 4, 6, 8, sulfur's got an octet. 2, 4, 6, 8, sulfur has an octet, but carbon does not. So that's probably not our best bet either. And if we look at the last one, we have everyone with an octet. We have 16 valence electrons. And that's going to be our best Lewis structure. Let's look at our formal charges for a thiocyanate ion. So I'm looking at sulfur. Sulfur should have 6 valence electrons. It's got 4 unbonded electrons and half of 4 bonded electrons. So that gives us sulfur 6 minus 4 minus 2. So that gives it a 0. Carbon should have 4 valence electrons. It's got no unbonded ones, but it's got 8 bonded electrons. That one should also be 0. And then our nitrogen should have 5 valence electrons. It's got 4 unbonded ones and 1/2 of 4 valence electrons, bonding electrons. So that becomes 4 minus 2. So that should be a -1. So we are looking for E, 0, 0, minus 1. Using the average bond enthalpies, go ahead and calculate the delta H for the combustion of acetylene. Now, this is how your question might show up. It might also show up where you have to draw out your Lewis structures, either one. What this is telling us is there's actually like a carbon right here in this joining point. And so this is telling us that we have a hydrogen to carbon bond. We have 3 carbon, or we have a triple bond between the 2 carbons. And then we have another carbon to hydrogen bond. The number in front is like our coefficient, so it's telling us how many of those molecules. So remember, for our bond energies, we want to think about bonds broken minus bonds formed. So for me to do this, I have to break the bonds from my reactants. So this one molecule has 2 C to H bonds, and we have 2 of those molecules, so there should be 4 carbon to hydrogen bonds. We have 1 C to C bond, and there's 2 of them, so we should have 2 triple bonds. We have 1 double bond of oxygen, and there's 5 of them, so we should have those that we need to break apart. Now, each of these molecules forms 2 C to O double bonds, and we have 4 of them, so we should take away 8. We have 2 O to H bonds, and so we should take away 4 of them because we have 2 of those molecules. And then we just need to put in their values for them. So I'm going to go ahead and take away that for a second so we can get a little more space in here. So this becomes 4, and our carbon to hydrogen bond we get from here, 414, plus 2, and the C to triple bond is going to be 837. We have our double bond for oxygen, 498. And we have our C double bond to O. And so when we add all of that together, we should get -2,428. And so that's how we can use our average bond enthalpies to calculate the delta H for that reaction. There's some more practice ones, so that way you can work through those on these next 2 slides. So go ahead and try that out for that one. As well as this one, there's an answer right after this. This is a little bit squished, so that should be methane, which is basically 4 single bonds around the carbon. Good luck with those. So today what we're doing is we're moving from Lewis theory to start talking about predicting molecular shapes. And so what we need to do is we use our Lewis theory and our Lewis structures to predict the number of electron groups. Now, these electron groups are the regions that the electrons are around the atom. So some of that, those regions are results of the shared pairs. So that's like the bonding one. Others are from the lone pairs, the unshared valence electrons. So both of those things matter. we're basically looking at how many different regions or areas we need to put our electrons in, whether that's going to be as a bond or as a lone pair. Now, the idea is that because our electrons are negatively charged, then the electron groups, right, whether they're lone pair or bond pairs, should repel each other. So we're going to use that information to kind of predict the shapes of the molecules. The atoms surrounding the central atom are going to be determined by where the bonding electron groups are. And in order for that to happen, they're going to try to minimize the repulsions between all of the electron groups. So the number of electron groups would tell us what kind of shape our molecule should take on as they try to spread out as far away from each other as possible. This is called the valence shell electron pair repulsion theory, also known as VSEPR. This helps us predict around the central atom where they're going to be as stable as possible. This is going to give us a series of geometric arrangements that's going to allow us to predict the shapes and the bond angles in the molecule, which kind of gives us a general idea of what they look like. The actual bond angles can vary just a little bit from the predicted ones because the different sizes and the different electronegativities of the groups do change things a little bit. But we're just going to keep them all as a standard for now. So if you imagine this is our central atom, our electron groups, right, these three here, you can see that they've kind of taken up this shape so that way they're spread out as far as possible. If we had them clustered together, similar to this, with this being our central atom, our third one could come in here, but it would be significantly closer to both of these than if they spread themselves out like this inside of a triangle looking shape. And so this is what VSEPR theory does, is it looks at that central atom, it looks at how many things we have to connect, whether that's lone pairs or bonded atoms, and then we spread them around. So the first part of VSEPR theory is we have to figure out the number of electron groups. So each lone pair, so that's a set of unbonded electrons, counts as one group. Each bond counts as one group. It doesn't matter whether it's a single, a double, or a triple, they all count as one. So really you can think of it, instead of as a bond, you can think of the number of atoms attached. So when we look at nitrogen dioxide down below, we have our nitrogen, and so we can say that our nitrogen has 3 electron groups. It's got 1 lone pair, it has 1 oxygen attached, and 2 oxygens attached. So it's got a total of 3 electron groups. It's got 2 atoms plus 1 lone pair, so it doesn't matter whether it's a double bond or a triple bond, we count those as the same. And so we're only counting the ones directly attached. So if you have like a chain of things, we're only looking at how many are directly around that nitrogen. Now there's 5 basic arrangements of our electron geometries. And this is because we're kind of looking at a maximum of 6 bonding electron groups for us. Right? There are much larger ones, but they're very rare, and so we're not going to worry about them for our class. And so these 5 basic arrangements gives us our 5 base geometries. And so each one kind of gets its own name. Now, when you have resonance, because it doesn't change the number of electrons or a number of things attached, it doesn't matter which resonance you use for your electron geometry, they should all be the same. If they're not all the same, then you don't have good resonance structures. So, looking at our, this chart pretty much sums up our basic geometries. Now, the first part, what we're going to look at is we're just going to focus on this section over here. So this is our electron regions. Our electron regions can also be called domains. They're also called steric numbers. And all of them are found the same way. It's the number of atoms attached to the central one plus number of lone pairs on the central atom. Right? So we're always looking only at the central atom. If you have two of them, then you're going to take on this electron pair geometry, linear. If you have three, you take on what we call trigonal planar. 4 is tetrahedral. 5 is trigonal bipyramidal. 6 is octahedral. Now, these you do want to have memorized. Having them memorized will just make the next parts, as we go through the shapes, much, much faster as you go through them. And so you really do want to have them memorized. The other part is that when you have something like trigonal planar, you have to use that name. It has to be trigonal planar. If you just put trigonal or if you just put planar, that would be incorrect. Same with trigonal bipyramidal. You have to have the full name. Right? So these are the ones that we will be using. Now, the nice part is if you have no lone pairs, their electron pair geometry is going to be the same as their molecular geometry. So we'll get into the molecular geometry in a little bit. Right now, what we're going to do is we're going to talk about how we develop these first electron pair geometries. So it gets its linear shape because if we have two things, the farthest apart we can get them is 180 degrees. So we take that carbon and we attach one of those oxygens, and we try to attach the other oxygen as far away from possible. So we go 180 degrees over to the other side, we draw it again. And so that will always give us a straight line. It gives us a linear geometry, similar to that. Trigonal planar comes from when we have our third group that we're trying to add in there. Instead of being a T shape where we have 180 and then two 90s, we try to spread that around evenly. So instead of being 90 degrees, we get 120. Now the difference between 120 and 90 is actually quite big for electron pair repulsion. Remember that your repulsion kind of goes up with a factor of r squared. So the farther apart you can get them, a much bigger impact does it have on your attractive force or your repulsive force. So that's why we would prefer for all three to be 120 degrees away instead of just 90. In your lab, you guys will look at how many are 90 degrees away exactly. Those are going to be our strong repulsions. And you can kind of see up here what they're doing is they're using these balloons to kind of symbolize the electron orbitals. And so you can see how now when we're set up with a trigonal planar, how we have space for each of those balloons to kind of find their way. Now from here, a lot of times when people say, well, if there's 4 groups, they come up with this shape here. They come up with a triangle. No, not a triangle, a square. But we have to remember that our molecules can exist in 3 dimensions. And so an easier one, instead of being a square, is actually to spread it out into what we call a tetrahedral. Now, each bond angle in a tetrahedral is 109.5 degrees. And this is an important bond angle. And it's something that you want to memorize as well. It's because it's the only one that's kind of funky. When we look at these, if we have a triangle, if we have a circle and we split it into 3 quadrants for its 360 degrees, that's how we can find the bond angle for a triangle, 120 degrees. If we split it in half, then we get 180 degrees. You hit half of your circle up, half of your circle down. So this 109.5 is our first one that doesn't add up to 360 degrees. And so it's an important one to remember, so that way you can know how it adjusts things. It gets its name tetrahedral because it looks a lot like a tetrahedron. It basically has each of those components. The only one that's missing is that it also has a central atom. The next one that we have is what we call a trigonal bipyramidal geometry. And how this one works is there's really a triangle that sits here in the center or the equatorial position, right? The equator. Above it, we have one position, and below it, we have one position. And so they get their names as being bipyramidal, is because you have two pyramids. They're both triangles. One's going up, and then the other one is going down. And so that's how it gets trigonal bipyramidal, right? You have a triangle, pyramid, and there's two of them. Now, the important to remember about your trigonal bipyramidal is that your center ones are of a little bit more space between them than your axial positions. So the one on the axis has 90 degrees from the equator, and the ones at the equator have 120 between them. So what we'll find out is when we add in our lone pairs have to exist in certain regions because not all 5 of these positions are equal. Some of them are closer to the other ones, or are closer to each other piece than the others. Our trigonal bipyramidal shape is when we had 5 regions. When we have 6 regions, we're going to move into this octahedral shape instead. Octahedral, instead of being a triangle at the equator, turns into a square. So the nice part about an octahedral is all of its bond angles are 90 degrees, and unlike the trigonal bipyramidal, all of their positions are equivalent to each other. And so this is an octahedral. And you can kind of see how it's got this square here, right at the equator, and then you have your 2 axes. Now that square looks the same whether it's that way or whether it's this way, because they're all 90 degrees apart. It doesn't matter. Now, normally in lab, what we would be working on is we would have a modeling set to kind of work with this. But to kind of help you, since we don't have a modeling set, is I've gone ahead and I've linked an online one in today's lab. So if you're more of a visual person, you would like to see these things added together and to be able to spin around your molecules, then you want to look at your lab today inside that online simulation. Now, what we had shown you were all of our electron geometries. So these are our electron geometries. This is when we treat them all as being the same, whether a lone pair. There we go. Now I got the pen back. So whether you're a lone pair or atom, we're treating them the same. So it doesn't matter where those regions are coming from. They will always start off with that same name for their electron pair geometry. Their molecular geometry is different, and so you want to make sure that you're paying attention to your questions about what they are asking you for. Are they asking you for your electron geometry, or are they asking you for your molecular geometry? It's very different. Sometimes they match, but a lot of times they're going to be different. And why is because of the lone pairs. So the molecular geometry can be different because when electron groups are attached to atoms of different size or bonded to one atom, they can be different in how they impact the molecular geometry. The biggest one that we're going to be worried about for our class is lone pairs. Lone pairs really impact our molecular geometry because they occupy space on that central atom, but they're not really seen when we're doing the naming. An example of this is going to be our tetrahedral here. When we have no lone pairs, we take on this tetrahedral that looks like this. But when we have one lone pair, you can see that this space up here is being occupied by a lone pair. And so when we name it, we're going to try to name it just using these 3 points. Later on, this one has 2 lone pairs, and so we're missing this section here and this one there. And so we're going to try to name this one using just these 2 atoms. And so lone pairs drastically change the names of our molecular geometries. You can kind of see it here as well. Each of these should be 120 degrees apart if they were all perfect. But because this oxygen's double bonded, you can kind of see it squeezed down here a little bit, and that's going to squeeze these to be a little bit tighter. So when we talk about bond angles, we're just going to assume that they're all ideal, except for the lone pair impact, which we're going to talk about. Now, while your different groups do matter, lone pairs have the largest impact. And the reason why is they're considered to occupy more space in a way. Now, their electron density is exclusively on the central atom. So unlike a shared one where they spread them out, our lone pairs are just focused on that central atom. So the relative sizes of the repulsion forces, our lone pair is our biggest repulsion. So we definitely don't want our lone pairs to be very close to our other lone pairs. We would like to get them as far away from each other as possible. The next impact that we're going to try to lower is our lone pair to our bonding pair. And then lastly, we're worried about the bonding pairs being close to each other. So as we walk through your lab today, you're going to have to be mindful about where you choose to place your lone pairs and your atoms, because we're going to try to minimize these interactions. We're going to minimize the lone pair versus the lone pair, bonding pair, and then the bonding pair is our last one. And this is a visual that helps you see why lone pairs have so much more of an impact. Bonding electrons are shared between two atoms. So you can kind of imagine that these two electrons are spread out evenly between these two nuclei. So some of the negative charge is removed from this central atom here because it gets pulled towards that other nuclei. On the other hand, when we have non-bonding ones, this one over here on the right with a lone pair, we have the same number of electrons, still 2 electrons, but now instead of being spread out evenly between the two nuclei, it's centered just around that central atom. So it's taking that same amount of charge, but squishing it down into a smaller amount of space. And so this is why it's more repulsive than our bonding ones. And you can see that it really does start to change our angle here. Instead of being 109.5 degrees, each lone pair kind of takes it down about 2.5 degrees. So what you do want to know is that your lone pair decreases the bond angle of the remaining atoms. More lone pairs, the larger the decrease. So if I had asked you about the bond angle between CH4, NH3, and H2O, we should know the bond angle of this as being 109.5. We should know that NH3 would be less than CH4, and we should know that H2Os should be less than our NH3, which is also less than our CH4. Now, because of this, we start to get more names for our molecular geometry than we did from our electron geometry. And so that's why we have this chart here, is that now as we start to name them, we have to come up with more options. So when there's no lone pair, our molecular geometry matches our electron pair geometry. You can see it's linear here for the electron, linear here when there's no lone pair. When there's one, it starts to change how we name them. So the first one is, if we look at our trigonal planar, if we add in one lone pair, we're going to try to name this shape left over. And you can see it kind of looks like a V, and that's how it gets its name bent. The next one down, when we look at our electron geometries, with this lone pair, our tetrahedral no longer has that fourth one, and so it's called trigonal. But because these are pushed down just that little bit from the central atom, we're going to call it pyramidal. So it's going to be a trigonal, a triangle pyramid. And so that's why we have to have both of those terms, because if you just say trigonal, I won't know if you mean planar or pyramidal. So you always have to include those two terms. When we have two lone pairs, when we start a tetrahedral, we make that V shape again, and so we call it bent. Now, while they have a similar shape, their bond angles are going to be very different with these bents. This one is much closer to 120, so it's a little bit less than 120 degrees. This one's closer to 104, right? So it's about 109.5 minus about 5 degrees. These next ones down here, this is going to be what we call a seesaw in your lab. They also call them a sawhorse. Both of those would be accepted. This one now takes on the T shape because you can see it actually has those two 180 degrees apart. We have the other one 90 degrees. And if we replace enough of them, we actually do get a linear shape back again. For our octahedral, the first one that we replace is called square pyramidal because you kind of have a square base down here. Plus you have that one on top giving you the pyramid shape. This one's called square planar because we finally get that square all aligned inside of the plane of the central atom. And then our third one, we're back to our T shape. So there is a lot of overlap with these names. The ones that I expect you to memorize are going to be these four from up here. Or sorry, all the way up to electron groups. So while you need to know your electron pair geometries, for all of them, these ones over here, these molecular geometries for these last ones, you don't have to memorize. But you do want to memorize that top section as we start going through our names. Now, the molecular geometries, we want to start off with where they initially started from, so the ideal one. So we're going to look at the first one, which is going to be our bent one. So our ideal geometry looked like this with 109.5 degrees. When we replace this top one with a lone pair, that lone pair is going to increase our repulsion. Right? That's going to push these other ones down. And if we push those down, then they have to get closer together. And so its molecular geometry becomes trigonal pyramidal because they're pushed down below that same level of that nitrogen or that central atom. And then their bond angle is going to shrink. Another one that we're looking at is going to be our bent one. Now it's called a bent shape because it takes up similar to that V shape for its geometry. So now we've replaced two of these. And so we're left over with this V here. Now you can see that instead of being that 107 like it was in our trigonal planar, our trigonal pyramidal, we're down to 104.5. And that's because each time we add in a lone pair, it should shrink the remaining bond more and more because it's trying to get away from these two things more and more. And so that's our tetrahedral geometries. Trigonal bipyramidal and octahedral is when we get into a lot of the names. And so we get into what we call a seesaw or a or a sawhorse shape. We also have what we call a T-shaped, and then we can get into a linear. Now, The reason why this happens and why there's not even more options is because of the repulsions. So when we have our lone pairs are going to be added to the equatorial position. The reason why we add the lone pair to the equatorial position is that it has less lone pair to bonding pair repulsions. And you'll see this in your lab that you guys work through. You'll be able to play around with this and you can see where you should be putting these. When you do a lone pair at the axial position, it has 3 of these repulsions. Those repulsions are too strong, and so if we can minimize them, we would prefer to do that. This 120-degree distance really minimizes that repulsion factor from that lone pair. And so that's why we take on this seesaw shape, is because we have to add in that lone pair from the equatorial position. That also means that our second one is going to be added there as well. And now you can see quite clearly why we call it a T shape. So remember that every time you add in lone pairs at the equatorial position. In order to get those. So for this first part, when you're working through your molecular geometries, worry about your tetrahedral shapes. As we move on to your final exam, then we're going to start to add back in these other molecular geometries. So instead of trying to have you memorize all of them at the same time, we're going to memorize these for exam number 4. Sorry, that wasn't a sentence that makes sense. So don't memorize until exam number 4. For the octahedral, because they're square, it doesn't really matter where you're adding them in. You just have to know that the first time that you add them, in a lot of ways you can imagine that you start adding them in at the equator, it doesn't really matter, is that when you add in the first one, we're always going to get that square pyramidal shape. But when we add in the second, we should add it in 180 degrees apart. We would like to split those apart as far as we can. And so that's why we add them in 180 degrees. From there, the next one that we add in has to be 90 degrees away from that. And that's how we get the T shape. The one after that, 180 degrees from that one. And that's how we get the linear. So as you go through and you're looking at your, you're trying to decide where you need to put your lone pairs, put your lone pairs as far apart as possible. Or, sorry, there's a better way to phrase that. You want to put your lone pairs to minimize 90-degree repulsions. And the order should be lone pair to lone pair we really want to avoid, then your lone pair to your bonding pair, and then finally your bonding pair to your bonding pair. And that's basically our molecular geometries. Now, as you start to draw them around, you want to first start with your Lewis structure. If you don't know your Lewis structure, it will make it very hard to predict your shape. Once you have your Lewis structure, then you determine your number of electron groups, so that's your number of atoms, plus your number of lone pairs on the central atom. And then we can go ahead and use that to determine our molecular our electron geometries and then our molecular geometries. When you're trying to draw these out, there's a way to kind of help you add in that three-dimensional depth. Now, I'm not a great artist either, and so this does help me. What you want to think about is a straight line is used to indicate them all being in the same plane, so the same plane as the paper. Your solid wedge lets you know if something's coming out towards you, and the hash wedge is used to kind of push it inside your paper, kind of like this. So if we want to talk about a tetrahedral has a part up on top that's aligned with our central atom, and one of its bottom triangle type of part is also in the same plane. The other two, though, one of them should be coming forward out of that plane, and one of them should be going back into the plane. And so that's how we're coming up with our three-dimensional shapes. The naming system that we've come up with our geometries, this is good for our single central atoms. If we have multiple central atoms, then we have to name each one to give its geometry around it. So we would name for this molecule down here, we would say that the left carbon is tetrahedral. We would say that the shape around the right oxygen is going to be bent. And so that's how we can kind of work our way through that. You don't have to worry about the second part. It was back when I had a more complex figure in there. And that pretty much ties up all of our conversation on our molecular geometries and our shapes. On Thursday, or next lecture, we're going to come back and we'll be looking more on your polarity and then your hybridization. So you want to make sure that you practice those things. If you are still not comfortable with bond polarity, then that's something that you want to practice, and I've included those slides there. Make sure that you know if you can classify something as being polar covalent. And then we'll be moving on from that part because we're going to be getting into our molecule polarity. And so in order to do that, we do have to know our shapes. I would recommend starting your lab today. It's very good practice of what we just went over. And so it will be a good way for you to kind of apply this material.